In this video, we're going to try to prove that if we are given a sequence and it's convergent, then this limit L is unique. First, what do we mean by some limit of a sequence? We assume that this is our sequence and it's convergent to some L. Okay, so this is our L here. So that means starting from some n, all the terms of the sequence will be very close to L. Okay, so the difference between the two, the distance between the two will be this epsilon, and more precisely it will be epsilon over 2, any small positive number. Okay, so it will be trapped here. Un will be very close. That means it's trapped in this interval that's surrounding L. Okay, that means that given any positive number epsilon, there exists an n in n such that for all n bigger than this n, we will have un minus L is less than epsilon. So starting from here, beyond this one, we will have the distance between un and L is less than epsilon. So this distance here will be very, very small. Okay? So to prove that this limit, that this L is unique, we assume that this sequence has two limits, L and L prime. And we need to prove that L is L prime. How can we do this? We use some kind of contradiction to prove this one. Okay? We will assume that it has two limits and we're going to show that they are the same. That's the key when you have to show something that's unique. You assume that you have two and you prove that they are the same. But one key idea is that for any two numbers, let's say we have A and B, okay? If we have for all epsilon positive, A minus B is less than epsilon, then A and B are the same, are equal. Okay, no matter how small the epsilon positive, the distance between the two will be less than that. That means they are the same, that A and B are the same numbers. So this idea is helpful when we try to prove the uniqueness of the limit. Anyways, let's apply the definition of the limit of the sequence to this case. So we're gonna, given any epsilon positive, so for the first one, let's write it again here. So the limit of this one as n goes to infinity is L. That means for epsilon positive, there exists some n bigger than n such that for all n bigger than this number, un will be trapped in this L, epsilon minus L and epsilon plus L. That means the sequence will be close to its limit, will be very small, the distance between the two. So this is for L. So for L prime, so given the same epsilon, it can be any, there exists some n1 bigger than n such that for all n bigger than n1, let's call this one n0, okay, such that un minus L prime is less than epsilon. Okay, so graphically what we mean here by this is that, so assume that this is our L and L prime. So starting from some n0, so here they will be close. So this is L. So this is my sequence. Okay, so starting from n1, my sequence and L prime will be close too. So my aim is to prove that these two are the same. So this is n0, this is n1. Now, given this epsilon, so given epsilon positive, I need to choose some n. So which n, n0 or n1, from which I start having this closeness between n and its limit. So the best option is that to choose, okay, if we let n is the maximum of these two, which one is bigger. Okay, so the maximum n0 and n1, and for all n, because n is bigger than these two here and here, so n is bigger than n, we're gonna have this one. Let's see what we can have. So let's do the difference between L and L prime. So here I'm gonna use the triangular inequality. So remember that we have x minus y is less than x in absolute value plus y in absolute value. So here we know that the triangular inequality gives us x plus y is less than x plus y. But think of this minus y as x minus plus minus y. Okay, when you take the absolute value of y is just, the absolute value of minus y is just y, so you get x plus y. So that means x minus y is less, in absolute value, is less than x plus y. So here, I'm sorry, I'm gonna do an equal sign. So I'm gonna add and subtract minus un. So I'll add un minus L prime minus un plus L. So I did nothing, okay? So here I can rewrite this one as un minus L prime minus un minus L. Okay? So I'm gonna go back here and switch this choice to epsilon over 2. We will see why. Okay? It doesn't matter, but it will help us. Now I'm gonna apply this one here. So what's this one is giving me? So this will give me un minus L prime plus un minus L, according to here, to the triangular inequality. Now this one is less than epsilon over 2, and this one is less than epsilon over 2. That means this one, L minus L prime, is less than epsilon. That means I have for every epsilon positive, L minus L prime is less than epsilon. What did we say before? That means that L is L prime. That means the limit is unique. Okay? This is a proof of this uniqueness of the limit of the sequence. You can prove it in less effort, but you have to explain some steps. You can't just skip and go and anyway, we can clean this one a bit, but I'll leave it like this. So if you want to clean it, you just take whatever you want. But this is a clear explanation of why we have if we have a sequence that's convergent, its limit is unique. And I think it's clear. For me, I think that's all we need to do, and this will end our video.